Hello everyone. Today's topic is intramolecular aldol condensation. But before we start that, we'll solve the homework problems. In the previous lecture, I gave two problems as a homework to you. So first we'll discuss the solution to those problems. In the first problem, 2,2-dimethyl 1,3-propane diol. Now this is our molecule 2,2-dimethyl 1,3-propane diol. Okay. Now it can be synthesized by the reduction of a mixed aldol, that is a cross aldol reaction product, using NaBH4. Okay, so now this is formed by some reduction. Now if you do a reduction of aldol, means initially in the aldol you must have a keto group. That keto group will be converted to OH group because of the reduction. So because it is a symmetrical molecule, you can choose either OH group and convert it back into keto. So I chose this one and I converted this back into keto form. Okay, so this is the aldol product that is asked in the first option. Second, what two carbonyl compounds are required to produce it? Now see, in the two carbonyls we must have two separate molecules that will combine to form this aldol. Now this is your functional group, this is your alpha position, this is your beta position. Now always break the bond between alpha and beta, because alpha carbon attacks the other carbonyl. Now this carbon was having a keto group which later converted to OH. So always break this bond between alpha and beta. So what you get on the left side of this is only single carbon. Now single carbon containing carbonyl is only HCHO, methanol. And on the right side what you get is CHO, carbon bonded to two methyl groups and another hydrogen. Okay, now this is the second carbonyl. So whenever you are converting a final aldol back into its reactants, break the bond between alpha and beta. That will also, we'll discuss this in the retrosynthetic problems also. Second problem, we have to synthesize this particular compound starting from the acetophenone. Now this is our acetophenone. Now look, first thing, in the acetophenone, if you treat it with base, base is going to remove H positive from this because this is the alpha position. So one H positive is lost. So when base removes one H positive, what you get is PHCO, CH2 negative. Now in the final product we can see that this carbon has three CH2OH groups, means this carbon has lost all three hydrogens, means all these three hydrogens have been lost one by one. So let us start with one. Now this CH2 negative is going to attack some compound which will form CH2OH. Now this CH2OH is coming from another carbonyl. So here, since we have only one carbon, so the carbonyl must also contain only one carbon. It means it must be HCHO. So now when this attacks on the HCHO, the final product is this molecule CH2. This will become CH2O negative and finally gets the hydrogen back, OH. Now we have been able to get one CH2OH. Now these two hydrogens must also be replaced by CH2OH, means we need to carry out two more steps with HCHO. So we need to repeat this procedure until all three hydrogens have been replaced, and this is the product you get. So this reaction will involve three aldol reactions or three aldol condensations between acetophenone and HCHO. Okay, three steps. So this kind of question can be asked in the JEE. This year also in the JEE main they have asked a question which the options were whether the formation of this particular compound will involve 3 aldol plus 1 canizaro, 2 aldol, 2 canizaro, kind of that. Okay, so you need to understand this kind of mechanism. Now, the intramolecular aldol reaction. Now, as the name specifies, intramolecular means we are not reacting two different molecules here, but the same molecule, within the same molecule, the reaction is taking place. That is why it ultimately forms a cyclic structure. So it is also known as aldol cyclization. So we need a dicarbonyl compound like this one. So this chain has two carbonyl groups. It's a dicarbonyl, and it can be used to make 5 or 6 membered rings. Why not 7? Why not 4? Because 4 membered or 3 membered rings have very high ring strain and angle strain, and the 7 membered also, they are having strain, and because of the large size, the geometry is not very stable. So we always try to form a 5 or 6 membered ring. Bigger than that we avoid, smaller than that we avoid. Now this particular dicarbonyl can be redrawn like this. Okay, now this make it more easier to understand the mechanism. Now this OH negative, now how many alpha positions we have? We have one CH3 here, we have one CH3 here. Now this position is alpha, this position is also alpha, this position is alpha, and this position also alpha. So we have 4 alpha positions. Now imagine you remove a hydrogen from this position. Here we form enolate. Now this enolate is going to attack the other keto. So it is going to attack like this, which will ultimately result in a 3-membered ring. That is unstable, so we are not going to do that. Next, suppose you form enolate here. Again, this is going to react in the same way and form a 3-membered ring, which is again very unstable. So the options of using these 2 alpha hydrogens can be discarded. Now these 2 CH3, now since they both look same, so you can use either one of them. So OH negative takes 1 H positive from this. So what we get here is CH2 negative, and now this CH2 negative is going to attack this keto group. So this is going to attack here, double bond moves up, so you get a 5-membered ring here. So here we have a CH3, and this O negative finally gains hydrogen and forms OH. So starting from this keto, this is the alpha position, this is the beta position, so you get a beta hydroxy carbonyl group, so you get a aldol. Now if the dehydration is carried out, means you have a OH negative, a little more concentration of base, then that will result in the dehydration. So alpha beta unsaturated product will be formed. So this will be the final product. Okay, so in these cases, first you redraw it in a more easier way, then analyze all the alpha positions and see which attack will lead to a 5-member or 6-membered ring, and then accordingly you carry out the reaction. Okay, what other variations are possible, we'll see in a while. Now why these 5 or 6 members are more stable? Because of unfavorable entropy and energy of larger and smaller rings. If you have a ring larger than the 6 carbon or smaller than the 5 carbon, then they have unfavorable entropy and energy factors. That is why thermodynamic constraints do not permit us to make those at the major product. Now in this particular question, 2,6-octane dione, we are acting it with OH negative, and we will be able to form 2 products. Now we have to form these 2 products and analyze which is going to be the major product here. If you number this chain, now we can have enolate formation at either C1 or C7. Okay, we can remove from this alpha or from this alpha. Why not from 3 and 5? Because I told you earlier, if you remove enolate or hydrogen from 3 position and attack this carbonyl group, then 1, 2, 3, 4, you are going to end with a 4-membered ring. Same if you form enolate at 5th position and attack this keto, then 1, 2, 3, 4, again you are getting a 4-membered ring. Okay, so that is why we chose 1st or 7th. So either you get a enolate at C1 or at C7. So let us form the 2 products. Okay, so first let us say enolate at C1, okay, attacks C6. So you have this CH2 negative enolate here. Now when this is going to attack here, how many carbon ring you will get? 1, 2, 3, 4, 5 and 6. So you can directly write it as a 6-membered ring where randomly you make this O negative, means OH anywhere. Now when the ring is formed at the same carbon where the OH is there, we also have a CH2 CH3 group, that is a ethyl group. So you need to attach CH3 CH2, that is ethyl group also. Okay, now this carbon is attacked by this alpha. Now so at this position we must have our keto, because we always get a beta hydroxy. So if this is alpha, this is beta, or you can also attach this keto group at this position. Okay, so now this is our product, this is our aldol. If you're going to carry out dehydration further, removing water from this, then we'll be getting this OH and H will be removed, and we'll have alpha beta unsaturated, and here we have CH2 CH3 group. So this is our A. And second option, if you form enolate at C7 and it attacks C2, then what happens? Directly you need not draw the whole thing again. From the 7 to 2, 1, 2, 3, 4, 5, 6, again you have a 6-membered ring. Draw carbonyl anywhere at beta position, you will have OH. Okay, that is certain. Now this one, because 7 is attacking at C2. Okay, so if this is the keto group, now this is the 6th carbon and this is the 7th carbon, it has attacked the C2. So where's the first carbon? It is outside of the ring, because this is going to join directly with the 7. 1 will be outside, so CH3 remains outside. Okay, so this is your beta hydroxy product, this is your aldol. And if you proceed with the dehydration step, then what you're going to get is alpha beta unsaturated. Now this is your B. Now you have to decide which among these two is major product. Are we missing anything in this? Whenever you solve a big problem, a big chain problem, always count the number of carbon atoms. How many carbon atoms here? 8. How many carbon atoms here? 7. So we are missing out on carbon. Okay, so on this keto, the CH2 attaches, but CH2 is also not CH2. This CH is also attached to one CH3 group. So here we have one CH3. Okay, sorry I missed it. So always in the end of the problem, make sure you count all the carbon atoms. Okay, so now we're done. Here also we have 8 carbons. Now, in the final product, this double bond is more alkylated. Okay, so B has more alkylated double bond, and the more alkylation we have on the double bond, more stable the alkene becomes. So this is more stable. Here is double bond is less alkylated. Okay, so one factor is the alkylation of the final alkene, final double bond. Second factor, we need to consider the nucleophilic attack. In the first case, we are attacking, this nucleophilic is attacking here. Now this carbon is bonded to a bigger ethyl group on one side and the chain on this side. In second case, when this nucleophile attacks here, on one side it has only methyl group and the same chain on the other side. So the chain on the side is common to both structures, but here on the one side is ethyl, here on this side is methyl. So definitely we can say that the attack of C7 enolate at C1 is less hindered. Okay, so these are the two factors. So you have to consider the hindrance while carrying out the nucleophilic attack, and you also have to consider the final stability of the alkene if you are going for dehydration. So finally B is the major product here. Okay, so this was a good question. Now let's move on to the next part, that is the last part of the reaction, retrosynthetic analysis, that is finding the reactants. You have been given the product, you need to work backwards and find out which molecules reacted together to give this product. Okay, so first step here, identify alpha beta positions. Second step, break the bond between alpha beta. Okay, so in this case, this CHO is your functional group. Now this is your alpha position and this is your beta position. Now don't tell me that this is your beta position, because we are talking about aldols here and it is always beta hydroxy or alpha beta unsaturated. Okay, so this is the alpha beta bond. You just break this bond. So these should be the two molecules. Now this OH was earlier double bond O. Okay, both were carbonyl. So what you get here is, this was CH2 and CHO plus. Now this alpha position, when you are breaking the bond, carbon should have 4 bonds. So you add 1 hydrogen here because that was lost. Or you can just say this hydrogen came from this carbon. So it will be CH2, this molecule, and CHO. So this is the reactants. So that is the retrosynthetic, simple thing. Here also, this is the CHO functional group. This is your alpha position. This is your beta position. You break the bond here. So what are you getting? H plus this one. In this case, this is your CHO, this is your alpha position, this is your beta position. So what you are getting is CH2, CHO plus okay. So you can see how easy this retrosynthetic analysis is. Here again, now here we don't have the aldol product, we have the dehydrated product. Same thing again. This is your reference point, this is your alpha, this is your beta. When you break this bond, now the left side has oxygen but right side doesn't have. Okay, what you removed is water. It is a product of dehydration. So what you do, on the right side which doesn't have oxygen, you just add oxygen. So you break this bond, give this side oxygen and give this side 2 hydrogens. Okay, let me draw this in a little emphasized way. So here we are. So when you break this bond, the right side doesn't have oxygen. So you break the bond and add 1 oxygen here and add 2 hydrogen here. So you are just adding H2O. So when you do this, what you get is this benzene ring, and this carbon already has 4 bonds. Now we are breaking 2 bonds and adding 2 hydrogen. So this is your CH2, below is CH3, plus here we are getting oxygen. So just form this like O. Here you have CH2, CH3. Here you have this benzene. Okay, same thing. Alpha beta, break the bond, add oxygen here. So PH, H, just you add oxygen. Here you add 2 hydrogens. So this will become CH3, CH3. Here this is alpha, this is beta, you break the bond. Now this is a result of intramolecular. Okay, so when you break the bond, you're getting this product. Okay, because alpha beta bond breaking and this OH is converted into double bond O. That's all. Next, 7th. Now, here, when you break this bond, on upper side, there is a keto group. But here, we don't have oxygen. So, beta position is always the one where hydroxy was. You have removed OH from here while dehydration. So you just put back that OH or that keto group. And this carbon has 3 bonds. To complete the valency, just add hydrogen. So this is the dicarbonyl. Here you break this bond. So what you get is left side doesn't have oxygen, so you give it oxygen to breathe, and right side doesn't have hydrogens, so you give them hydrogens. So it is PH, C double bond O, CH2, CH3. Okay, so that's all. So you can easily solve the aldol problems. Okay, so I hope you are a bit more confident about this particular reaction mechanism, and this mechanism is not only going to help in the aldol, but a general mechanism helps you in many questions. Okay, now in the next lecture I won't be discussing something new about this aldol that is important for JEE, but yes, we will be focusing on some key points that you must know if you are opting for the JEE advanced. Okay, some in-depth points about the aldol. So if you are preparing for JEE advanced sincerely, then we'll discuss some more points in next lecture. Okay, so see you till then. Thank you.